Thanks for coming. My talk is about general relativity with variable speed of light. The question that comes up is, isn't relativity about a constant c? Isn't this the last thing Einstein would have appreciated? And the answer is no. It's the very first idea he considered when he started to think about general relativity.
When he considered this possibility, he said simply, okay, we have a situation as in optics, light, there is a refractive index which is influenced by the vicinity of masses, and if you assume that the speed of light is lower in the vicinity of masses, you get the very same deflection of light. That's what he said in 1911. The idea goes back to 1907, and I will talk about the historical details tomorrow in a talk of the history section. But, well, I'd like to present the idea to you today. So, let's go ahead. You might ask, doesn't general relativity talk about a curved space? Does this analogy of optics really explain general relativity? But I gave you an example of a curved space here. It's building, and actually, if you don't move straight here because it's not the same velocity everywhere. Instead, if you want to go the fastest path, you have to choose the roads, of course, because the velocity is higher there, and so you get a curved path if you move along. So so you might express a flat space you might express a curved space as a flat space with a variable speed of light. And this is actually the same description, and you might ask, okay, why the speed of light isn't this a measuring value? No, it's defined by our unit system, and once you change the speed of light, of course, the wavelength and the frequencies have to change accordingly. So you don't note it locally, but you can describe a curved space with a variable speed of light. So I think this still sounds odd to you, but actually that's what in every textbook of general relativity is. There is nothing strange about. Note that the photon speed is 1 plus and a term that involves the gravitational potential. That's what Weinberg says, and so on, from Eddington to the modern ones. It's clear that the variable speed of light is a feature of general relativity. It's just little known that the formalism is indeed equivalent. And this is very nicely explained in a paper by a Belgian physicist. He proved that it's indeed equivalent in the 1p limit of general relativity. And you might wish to read this paper, but I'd like to show you, just give you some visualization that how it works, how the classical tests are satisfied. If you assume that, we have all this here. Okay. If you assume that indeed the speed of light is changed in the vicinity of masses by a factor alpha, which depends on the gravitational constants, then this change is distributed to the frequencies and to the wavelength equally, and that's all what you need to explain the classical tests. So you should mind that propagating light instead keeps its frequency, and all the change goes to the wavelength. That's simply because, as in optics, you don't change the frequency, you just change the wavelength. If you go to another medium. So we have light deflection here, and that's what Einstein said in 1911. By means of Huygens' principle, light rays propagated across a gravitational field undergo deflection. And the second test, we would think about de Broglie wavelengths. Oh, sorry, it's a little slow. And we can talk about this a little bit. In the gravitational field, the wavelength is reduced because the frequency is reduced, the wavelength is reduced, and the speed of light is reduced twice, so to speak. But propagating light must keep its frequency, so all the change goes to the wavelength, and if a wavelength comes out of a gravitational field, it appears to be longer, and that's the gravitational redshift we observe. Okay, so I'm just going through the tests. Shapiro time delay, which was discovered in the 1960s. Also, this is described by a slower speed of light. And eventually we have the perihelion shift of Mercury. That requires a little bit more detailed discussion, because you have several terms here that contributes. But once you live in a world with a variable speed of light, all the quantities have changed. You have different time scales, different frequencies, different wavelengths, and accordingly different scales for velocity, acceleration, and even mass, because mass is proportional to an inverse acceleration due to Newton's law. So that's a little overview about the quantities, how these quantities change in the gravitational field. You might note that mass appears to be bigger because it has a higher inertia, because wavelength is reduced, the frequencies are reduced, so every measure of acceleration is reduced to the third power, so masses appear to be bigger. Okay, this is an important point I'd like to stress, because until here there is nothing to discuss. It's just another version of general relativity, and it depends a little bit, if you want, on your mathematical taste, which one you like. And or what I forgot to say earlier, it depends on the metric or on the connection. How you define the metric, you can define it according to the real length, or you can define it with respect to the time. So until here, it's just the interesting fact that you might describe it with a variable speed of light. But once you think about a variable speed of light, this approach suggests that you go beyond general relativity. And I'd like to mention Ernst Mach. And we know that Einstein was very influenced. He admired Mach, and his writings he was very intrigued by his publications. And what is today called Mach's principle is the hypothesis that gravity is related to all other masses in the universe. But of course, at Mach's time, that was very difficult to quantify, and it was never properly included in general relativity. But several researchers continue to be intrigued by this possibility, among them Dirac with his cosmology in 1938, and the British Egypt cosmologist Dennis Sharma wrote a very interesting paper in 1953. And first of all, there is Robert Dicke, who became later famed for his contribution to the cosmic microwave background. But he wrote a very interesting paper in 1957, and Well, there are actually two big achievements of Dicke, because first of all, why Einstein's variable speed of light theory didn't get much attention? Because it contained a little error. Einstein thought that all the change of the speed of light was included in the clocks, in the frequencies, but he neglected the length scales. And it was Dicke to discover this error and to correct it and to give a simple formula that fixes everything. But that was almost 40 years ago, after the big success of general relativity, so nobody noted it. And it's, by the way, not the same thing as the so-called Browns-Dicke theory. It's still another thing. So that was Dicke's first big achievement, and he calculated this index of refraction, that the ratio of the two speeds of light in the vicinity of a mass. And he said, okay, the variation in index of refraction about the sun is required. Obviously, the right term is related to the gravitational potential of the sun. And this is a small term. Sorry for the mess here. Couldn't it be that the right term, does it have its origin in the remainder of matter in the universe? And this is a truly revolutionary idea of Dicke, because it includes Mach's principle in a quantitative way. That's the first quantitative formulation of Mach's principle. And I think it's just a wonderful piece of reasoning. He said, okay, this is a small term. It's related to the sun, to our solar system. Couldn't it be that we are fooled by this one? This one is not true, but it corresponds to the sum of all other gravitational constants in the gravitational potentials divided by the speed of light. So let's think about this hypothesis a little bit of Robert Dicke, and it can be reassumed in this formula. C squared, the local speed of light, is C0 squared as a constant divided by the sum, divided by more or less, this is the gravitational potential. And well, I mean, let's show you at least a little bit how Newton's law drops out here. I know that nobody pays attention to the technicalities, but if you start assuming that c squared is indeed this sum, and if a consequence would be that the conventional gravitational potential is 1/4 of c squared, so you can calculate the local acceleration by taking the derivative. So what happens if you put this in the derivative? It goes to the denominator, and then of the third line, again, you replace it, and you end up with this formula, Newton's law in first approximation. You see the inverse squared law, and this term, surrounded by the red line, corresponds to the gravitational constants. That's the very revolutionary idea of Dicke, how to realize Mach's principle. He said that the gravitational constant might be not a true fundamental constant. It might be that it can be calculated by all other masses in the universe, as it was suggested by Ernst Mach back then. So, here we are. Why we need that? Because it's a very nice formula, but it doesn't really resemble Einstein's equations, which are written here and elsewhere. And what can we do? Until here, it's nothing new in my talk, by the way. But actually, my student, Jan Preuss, he has also gone to the German contest of young scientists with another project on quasars. And he had a very nice idea how to reformulate that formula of Robert Dicke. And if we start by Einstein's gravitational constants, which is just AP Newton's constants divided by c to the 4th power. Well, this is just rewriting the other formula, but now mind the third line. 1 over c squared is essentially this sum over all masses in the universe divided by the respective radius. And of course, you can replace this sum by an integral. That's nothing new, so to speak. Oh, I have to speed up, sorry. So we can apply the Laplacian, and we can apply Green's functions. If we apply Green's functions, it turns out that all these integrals simplifies very much, and we end up with a very simple formula for the Laplacian. And if you multiply it by c squared, so this would be a very intriguing form, which is not really the same thing about the Einstein equations, but you remember Einstein equations, the Einstein tensor is nothing else but the Laplacian with covariant derivatives, with a second covariant derivative. So actually, this is a local form, and it contains the fact that the gravitational constant can be calculated from the masses of the universe, but in a very subtle and intriguing way. And there are no constants at all, and the space-time curvature, which is 1 over square meters, is simply contained in the derivative. So I think this is an intriguing possibility. It encompasses Mach's principle. The other things I think I already mentioned. And also Einstein was aware that at the very end you had to express a theory of variable speed of light with a differential equation of this kind, and he postulated another one. I don't think this is the only one. There is another very interesting one. So you showed me 1 minute, right?
Yeah.
So well, I can continue half an hour, but I don't think everybody would appreciate.
Depends if you want some discussion.
Yeah, and maybe we'll leave some time for the discussion, and I skip over briefly. I'd like to just to mention that there is a very interesting relation to Dirac's large number hypothesis, and well, this is again the formula, and well, just I'd like to mention one thing. Everybody says, hey, okay, inflation explains the flatness of the universe. Well, inflation didn't explain anything, because the flatness of the universe was discovered by the same Robert Dicke in 1969, 15 years before anybody talked about inflation. So it's very strange that the universe appears to be flat, but you shouldn't do a post hoc patch to fix the theory. Calculating the gravitational constants would mean you have a flat universe by construction. It would be a logical necessity if you have this. So, in fact, that made up my mind a little bit about inflation, and I agree with Roger Penrose that even artworks find their offspring are beautiful. And I think I skip over the last part about the cosmological evolutions. There are a couple of things to mention, but okay, we can leave this to the discussion. And it's also in my paper in Annalen der Physik, where you can read it. So the really interesting thing is that we have a kind of explanation of the Hubble redshift, and you agree with Dirac's hypothesis. So, to conclude, general relativity and variable speed of light was Einstein's initial idea. It's determined by the distribution of masses. It suggests an elimination of the gravitational constants. It would be would explain the flatness problem by construction. And while in agreement with the classical tests, it offers an alternative cosmology. I think we are severely underestimating Einstein's variable speed of light approach. Maybe his first idea was the best one. Thank you. You can read this in Annalen der Physik, and you can read a popular version of this in my book Bankrupting Physics, which is an edition of the German Science Book of the Year. And also in this last book, there is in part 7 an explanation of this idea by Robert Dicke, and I think there will be a follow-up. Thank you very much.
Thank you for the talk. I think we have time for one question or comment. Yes, please.
This idea of Dicke's, this idea suggests that the gravitational constant should vary on a Hubble timescale, as opposed to a link of gravity with the
Yes.
universe. Unfortunately, latest observations, especially using current data from Mercury Messenger spacecraft, show that the upper limit on the variation of G is a part in 1,000
Yeah.
of the timescale.
Yeah, of course. But that was not Dicke, that was already Dirac in 1937, 1938, who suggested that once you talk about this hypothesis, he said that would be a necessary consequence. Okay? So the idea goes back to Dirac. And Dirac said, okay, we have this observation of the strange number of electric and gravitational force, and we have the same number, 10 to the 40, as the radius of the universe and the radius of the proton. So, and he wrote that he believed that the gravitational constant would decrease, and as you say, observational evidence didn't show such a decrease of the gravitational constants. But once you live in this world of changing constants, you cannot talk about an isolated change of the gravitational constant, because you have changing accelerations, changing masses, and changing various timescales. So it's not obvious, and it's not obvious that you observe. You have an observed change of the gravitational constants, because one thing is to talk about the observation of the observed quantities, and another thing is about the other ones. Okay?
Okay. One short question.
When I look at this Jan Dicke formula, are the dimensions really right?
Of course. Physical dimensions are my favorite subject. Should I go back? Which dimensions you're concerned about?
You say c squared is c0 squared divided by the sigma and...
Yeah, okay. You're right in the sense that this refers... where's the formula? Here, on top. Yeah, that's correct. I mean, that would need to be expressed in reference to the mass of the universe and the radius of the universe. But if these are relative units in relation to the mass of the universe and the radius. But if you put in another, it just cancels out if you take the gradient. Yeah.
I see. The dimensions of the C0 is not the same as the dimensions of the C?
Yes, it is. Yes, it
So,
is. But the other ones are normalized. So m would be the usual mass divided by the mass of the universe, and r would be the radius divided by the radius of the universe. Okay? So it's normalized in this case. But you're correct in observing it.